Fusion APUs with very high performance, single precision and double precision support. So this slide should look familiar. You know, it talks about this movement from the single core era that was driven primarily by frequency, which was very nice while it was in that active, very steep slope, followed by the multi-core era, which has been very nice for several years. In fact, the multi-core era has been very good to AMD in the area of HPC. For the past 7 years in running, we've been on the top 500 list with a great number of systems and a very popular choice for HPC vendors. And now going forward, because of some of the constraints associated with chip multiprocessors, we're going to this heterogeneous compute era. This is a recurring theme, and I'm simply repeating it in case you've been hiding under a rock for the past 10 hours. This is a slide directly out of Phil's keynote this morning, and it talks about these different eras of GPU offload. And again, subtle but very important points here. We're moving from kind of a very hacker mentality, make your program look like it's a graphics kind of thing, to something that's very driver-centric, a little bit better programming model and programming interface, but still the GPU is a driver. And then with the FSA architecture, we're moving to a model where the GPU is now a first-class citizen. It's at the same level, if you will, as the CPU. What about this exascale thing? You probably have all heard about the exascale initiative, either in the US or more recently there's been some publicity about India, but there's also a European effort and an Australian effort. DARPA promoted a study or sponsored a study in 2008, and they produced this 100 or 200 page paper, which is available at the site mentioned here. And they really brought out several really interesting challenges, but really they kind of fall into these 4 buckets. Energy and power. They want to limit the exascale computer to about 20 megawatts. It costs about $1 million to run 1 megawatt. So that means running this computer would cost $20 million a year. If it was 100 megawatts, it would cost $100 million a year. So getting the power down is really important to the mission they're after. Memory and storage, concurrency and locality, especially from a programming model standpoint, and then the resiliency of these exascale systems. So all of this is very nicely highlighted in this white paper, which if you're interested in this area, I would urge you to take a look at. In terms of AMD's capability and the kind of compute node that I could imagine to fulfill this, what we would be going after is about 20 picojoules per flop. Here we're talking about double precision flops. That would be about 50 gigaflops per watt, which would be about 10 teraflops in a 200 watt power budget. Again, these are double precision flops. And then deploying 100,000 of those actually gets you to 1 exaflop at 20 megawatts. So that's throwing around some pretty big numbers and making some big assumptions, but just for reference, today on the high side, a double precision floating point op takes about 200 picojoules. So we're talking about a 10x efficiency improvement at the very low level to make this go. However, we've been on a trajectory of improving at a rate that intercepts this point by 2018 or 2020. So we actually feel fairly confident about being able to do this. Interestingly, it will also require 100 petabytes per second of local memory. That's 1 terabyte per second per node times 100,000 nodes. So we're talking about extreme memory bandwidth here and extreme memory capacity. The programming model, we certainly envision to be a hybrid, which read that as FSA on heterogeneous nodes, and then with MPI as follow-up. MPI as the programming model for the large-scale clustering aspects. And while we're on the large-scale clustering aspects, we believe that PGAS-style messaging, partition global address space, which is a way of nodes communicating with each other in very efficient ways, that's the sort of messaging for underpinning the synchronization and data movement. And then finally, of course, at the system design, we need very low latency, high bandwidth node interconnects. Now, programming at scale, 100,000 nodes is pretty tricky on a lot of levels. Some of these hardware technologies present very different characteristics at the full system level. So, for example, you probably all have an intuitive sense about NUMA, non-uniform memory access, from a latency standpoint, but it also comes out in the form of bandwidth and coherency support. Another aspect of this, sort of, I don't want to call it NUMA, but differences at different parts of the system are the networking tiers. So, variable synchronization costs, variable communication costs, and so on. And then reliability itself. Nodes go down, they come and they go. So we can solve a lot of these problems with brute force, just brute force hardware, but at amazingly increased cost. And in many cases, it's not so advisable to do that. So the real answer is going to be a combination of hardware and software, which certainly has its pluses and minuses. Striking that balance is going to sort of be the defining characteristic of these successful exascale systems. In addition, I think abstractions that present these realities that software has to deal with in a realistic way is really important. So the ones I think in particular are the locality is something that really should be exposed to certain levels of software. You can't be, locality oblivious. Optimized communication, the checkpointing to support that kind of reliability that you need, and then the systems and resource management at scale. Some sort of system level hypervisor, if you will. So that's how you might think about, one of these exascale systems.